So we've been talking about polynomial functions, and I believe we defined what a polynomial function is. We talked about the general form of a polynomial function. And I believe we also talked about the right-end behavior and the left-end behavior of a polynomial function's graph. So getting back to the form of a polynomial function, we said, okay, anything that can be written in the form a constant times x to some big power plus a constant times x to a smaller power, and keep going on and keep going on and keep going on, is a polynomial function. It has degree n. So basically the largest power, n, is your degree. And these exponents here have to be whole numbers. So you can actually imagine the very last term, a0, that's a constant. a0 is a constant. You can imagine has an x to the 0 power there if you want. So it's still a whole number. So you have to have whole numbers for your exponents. That's key. And in front of each x to a power, you have a coefficient. These are the coefficients. And the leading coefficient, right? The leading coefficient is that an. So we say this one has degree n, right? This one has degree n. So that's called the general form of a polynomial function. Now, it turns out that you can factor your polynomials oftentimes. Now, some of them will not factor, but normally you can do some factoring. So, for example, if I had a polynomial function, I don't know, x cubed plus x squared plus x plus 1, right? This one right here. What I could do here, I could do some factoring. I could group the first two together, and I could group the second two together. Now, if you look at the first two that are grouped together, they have something in common, right? They both have an x squared in common, right? X cubed and x squared have an x squared in common, so I can pull out an x squared, factor that out front as the greatest common factor, and that leaves behind an x plus 1, right? X plus 1 times x times x squared, that's the blue x times the red x squared gives me x cubed, then the 1 times the x squared gives me the x squared. Okay, when I look at the second one, the second factor, the second blue factor, I look at what's in common between x and 1. Well, just the 1's in common. I can pull that out, and that just leaves me with x plus 1. So for f of x, notice they both, the first term, x squared times x plus 1, and the second term, 1 times x plus 1, both have an x plus 1 in common, so I'm going to take an x plus 1 out front. And that's going to leave me with, in parentheses, an x squared plus 1. So yeah, oftentimes you can do factoring. Now, you cannot factor this x squared plus 1. That's called irreducible. It's not factorable, so it's irreducible. Irreducible. That can't be factored. If you tried to factor it, you wouldn't be able to. So this is called the completely factored form. Completely factored form of the polynomial function f of x. Yeah, so we started off with, you can say the degree was 3, right? It's a degree 3 polynomial, and we factored it down. That's what we want to start looking at. We want to look at factored forms of polynomials, Now, in this section, we're not going to really focus on doing the factoring. We're going to focus on that in section 4.5, doing the factoring, but we want to discuss the factored form of a polynomial. So here's a definition. Definition. A polynomial f of x is said to be completely factored. That's what we're defining, completely factored, if f of x can be written as follows. p1 of x, that's a polynomial, times p2 of x, that's another polynomial, and so on and so forth, times pk of x. So basically, f of x, our big polynomial here, is a product of smaller polynomials, where each of these pi of x, I'm going to call each of these a pi of x. So p1, p2, p3, p4, all the way to pk of x, these are all going to be called pi of x's in general. Each pi of x is irreducible. That means completely factored. I mean, it can't be factored any further. So if you can take your polynomial f of x and break it up into smaller polynomials, where each smaller polynomial is not able to be reduced anymore, we say that's irreducible, then f of x is completely factored. Okay? So we want to think about something. How do you find the degree of a completely factored polynomial? So here's a this is not a definition. This is, I guess, a theorem about the degree of a completely factored polynomial. So here's the theorem. It says the following. If f of x, which is factored into p1 of x, times p2 of x, so on and so forth, all the way to pk of x, is completely factored, and with the degree of the first polynomial, p1 of x, if that's m1, the degree of the second polynomial, p2 of x, let's call that m2, and the degree, let's go a ... to say so on and so forth, until you get to the last subpolynomial, pk of x. We'll call that m sub k. So the degree of this first polynomial is m1, the degree of the second polynomial is m2, the degree of the third polynomial would be m3, the degree of the fourth polynomial would be m4, all the way to the kth polynomial, the last polynomial, we'll call that mk. Then what would be the degree of the entire polynomial f of x? Then the degree of the actual polynomial f of x is going to be the sum of all the degrees of the subpolynomials. So basically you take the degree of p1, the degree of p2, p3, p4, all the way to the last polynomial, pk, and you add those degrees up to get the degree of the entire polynomial. So let's actually see that in action. Let's say do a little example here. Let's say I have a polynomial f of x equal to 3x minus 1 squared x plus 3. Okay, so that's my polynomial. Now, right now, it's completely factored. It's in what's called the factored form. So basically, you have 3. That's just the constant out front. You have x minus 1 squared. That's a factor. And you have x plus 3. That's a factor. So what we're going to do, we're going to rewrite this, f of x. So we're going to leave the constant out front alone. That's just going to be a coefficient. And what we're going to do, we're going to take x minus 1 squared. So that means x minus 1 times x minus 1, right, times itself. And then x plus 3. So what I'm going to do here, I'm going to actually multiply the x minus 1s out. I'm going to leave the 3 alone. I'm going to take the x minus 1s and multiply them out, right? You basically FOIL. What happened there? You take x times x squared x times -1 is minus x. -1 times x is minus x. And -1 times -1 is positive 1. And then we're going to write x plus 3. Okay, so I'm foiling out, we call that foiling out the green. I still have to combine my like terms here, right? We have x squared. So when you combine these two terms, the minus x and the minus x, you're going to get minus 2x, and then plus 1, and then multiply that by x plus 3. Okay, so I've combined my like terms in the green. The green has been foiled out. Now we're going to multiply the green and the red. So we're going to leave the blue 3 alone. So let's take x squared times x is going to be x to the 3rd power. And then I'm going to take x squared times 3. It's going to give me plus 3x squared. Okay, then I'm going to move on to minus 2x. Minus 2x, I'm going to multiply by x. I'm going to get minus 2x times x is minus 2x squared. And then I'm going to take minus x times 3 here, and that's going to give me minus 6x. Okay, then I'm going to move on to 1. I'm going to take 1 times x. It's going to give me x. And then I'm going to finally take 1 times 3, and that's going to give me positive 3. I'm just doing a lot of multiplication here, polynomial multiplication. And now I have to combine my like terms with all that green stuff I have. They're going to leave the 3 out front. So I'm going to have x cubed, and now I'm going to combine, let's see, 3x squared and 2x squared. It's going to give me simply x squared. I'm going to combine here minus 6x and plus 1x. It's going to give me minus 5x. And I have a plus 3 on the end. So if I decided to actually continue expanding this, I multiply through by 3, right? I get 3x cubed plus 3x squared minus 15x plus 9. So this would be the general form. The general form, and you would see that the degree of this polynomial is, the largest power here is the power of 3. Now if I had used my theorem about the degree of a completely factored polynomial, how would I do that? How would I have used my theorem and come to that conclusion really quickly without having to FOIL that all out, expand all that? Well, I could have said, okay, so my first factor is this green one right here, right? This green one. So I could have said, okay, if I wanted to find the degree of f of x, let me write this again. Let me show you the quick way to do this. So if I wanted to find this the quick way, degree of f of x, well, I would first take this green factor. That has a degree of 2 on it, right? X minus 1 squared. So you take this degree here of 2, and then you move to the red one, which is what? X plus 3. That has a degree of 1, and you add them together. You take 2 plus 1, and you get 3. So, yeah. It's a quick way to do it. So rather than foiling things out and expanding out your polynomials in fact when they're in factored form to the general form, you can just add up all of the different degrees of the subpolynomials, or all the degrees of the factors. That's the quick way to do it. Okay, so just to make you aware of that, that's a really important skill. Okay, so that's what we're going to do next. Just do an example here. I'm going to say determine the degree. If I can spell degree, that would be great. Of each completely factored polynomial. All right, number 1, we have 5 times x minus 1 squared times x plus 4 to the third power times x squared plus x plus 1. So I'm telling you already, this is completely factored. You can't factor it any further. So all you have to do is find the degree of the polynomial. So all you're going to do, you're going to take each factor here, the red factor, the yellow factor, and we'll say this last one's the green factor, and we're going to look at the degree of each polynomial, each factor, basically. So the first factor has a degree of 2 out here, so we're going to take 2 plus. The second one has a degree of 3 right here, and then plus the last polynomial I circled in green, that has been completely factored, in the largest power there is the power of 2. So we're going to add all those up. So 2 plus 3 plus 2 is 7. The degree is 7. So rather than expanding all that, that would take a long time to FOIL all that stuff out, expand it. We can just add up the different degrees. So we get a degree of 7, a total degree of 7 for that polynomial. Okay, number 2. So I have negative 8 times x minus 1/4 to the 5th power times x plus 1/9 to the, no, just x plus 1/9. And then finally times x squared plus 2x plus 5. Okay. And what I'm telling you with this is that it's already completely factored. You can't factor it anymore. So if I want to find the degree of this completely factored polynomial, I'm going to look at each major factor. I'm going to take this first one, the red, the second one, the yellow, and this third one, the green. I'm going to look at the degrees of those and then add up the degrees. So the first one has a degree of 5. That's that big exponent out there. Plus the degree of the second one, this only shows up one time. It has you can imagine there's an exponent of 1. And then the last one has a degree here of 2. The largest exponent is a 2 there. So we're going to add that in, and you add those together. 5 plus 1 plus 2, I believe that's 8. Yeah, it's a degree of 8. Okay. That's the quick way to do it. All right, we'll do one more. And actually, this last one will be more like the ones that will be showing up in your assigned problems. 201 times x plus 8 to the 6th power times x squared times x minus 9 to the 3rd power. So basically, you have disregarding that coefficient out front of 201, you basically have red factor, yellow factor, and green factor, these 3 major factors coming into play. I wanted to find the total degree of this polynomial, the degree of the polynomial, degree of f of x. Let's say, okay, my first factor would have a degree of 6. That's the largest power that shows up. My second polynomial has a degree of 2. It's the largest power that shows up. And my third polynomial has a degree of 3. So I add up all the degrees of the factors, and I get a total degree of, I think, 11. 6 plus 2, yeah, 11. So probably you'll be seeing things more like this. So 11, that's an 11 right there. Okay, so we want to introduce some terminology here, Basically looking at some terminology. A lot of terminology to develop in this video. So these are going to be some equivalent statements. For what it means to be a zero of a polynomial. So we're introducing this term called a zero of a polynomial. What is a zero of a polynomial? So let's say, first of all, we have a polynomial. Let's call it f of x. Let f of x be a polynomial. The following terms are equivalent. The following statements. The following statements are equivalent. They mean the same thing. So number one, if I were to write x equals c, so c would be like a number. Imagine there's a number like a 3 or 4 or 25 or 10,988. That's what c is, just a number. So x equals c is a 0. We're defining this word called a 0. Or you can also use the alternative for a 0. Some people call it a root. You'll hear it called a root. So c, x equals c, is a 0 or a root of f of x. That's one way to make this claim. Now, what does that mean? Alternatively, that means x equals c is a solution to the equation f of x equals 0. So that's what it means for x equals c to be a 0 or a root of a polynomial function. It means that it's a solution to the equation f of x equals 0. So basically, set f of x, set the polynomial equal to 0, and when you solve, find all the solutions to that equation. Your solutions will be called the zeros of the function, or the roots of the function. Okay, an alternative way of saying this is x minus c is a factor. Is a factor of f of x. Yeah. So if x equals c is a solution to f of x equals 0, then that means x minus c is a factor of the polynomial function. Or another way to say this is c comma 0, that point is an x-intercept of the graph of f of x. Yeah, so basically a 0 or a root of f of x is the same thing as an x-intercept. Why is it an x-intercept? Well, when you set the function equal to 0 and solve for x, that's going to tell you where your x-intercepts are. Yeah, so this is some new terminology. We're introducing this idea of a 0. So a 0 is just a new word for an x-intercept, basically. So we've already looked at x-intercepts when we studied other functions in the past. Okay, so here's an important definition dealing with these zeros or these x-intercepts. Suppose I take a function, a polynomial function, f of x. So suppose f of x is a polynomial where x minus c to the m power is a factor of f of x, and x minus c to the m plus 1 power is not a factor. Of f of x. Then we say x equals c x equals c is said to be a 0, or we can also call it a root. It's another word we've seen, or a root of multiplicity m. For f of x. Yeah, that's what we're defining. We're defining being a 0 of multiplicity m. Yeah, so basically here's the idea. Here's a little example. So let's say I had a polynomial, f of x, that had a factor like this, x minus 1 to the third power, and then I had something else, I don't know, x plus 2, like that. We would basically say that x equals 1 is a 0 with multiplicity 3. Why multiplicity 3? Because you got that exponent of 3 out there. And for the second factor, x plus 2, so basically we take x plus 2. So imagine taking x plus 2, setting equal to 0, you get x equals minus 2, right? So you'd say x equals minus 2 is a 0 with multiplicity 1. Why would it have multiplicity 1? Well, if you imagine there's an exponent up here of 1. Okay, so that's what we're going to be doing here. We're going to be dealing with this, and we want to talk about what do the multiplicities determine. So we know that the zeros determine the x-intercepts. So basically these factors here are going to determine your zeros, which determine your x-intercepts. Well, what do those multiplicities determine? What do those powers determine, the multiplicities? They're going to determine how the graph behaves at the x-intercepts. How the graph behaves at the x-intercept. So we're going to write that down here. We're going to talk about characterizations. This is basically a theorem, characterizations for even and odd multiplicities. Okay, so let's suppose x equals c is a 0, or you could call that a root, or you could call that an x-intercept. So x equals c is a 0 of multiplicity m for f of x. So the multiplicity is m, it's just some number. If that number turns out to be even, if the multiplicity is even, then the graph kisses the x-axis at that place, at that x-intercept. The graph kisses the x-axis at x equals c. So if you have an even situation, you kiss the x-axis. What does that mean? What does that mean? We'll draw a little picture. So let's say my polynomial has c is the 0. So we'll write a little c here on the x-axis. If you were to have an even multiplicity, then the graph might do something like this. It just kisses it. It hits at c and then bounces back off. It just kisses it. Kisses it. Okay? And 2, what happens if m is odd? What if the multiplicity of that 0 is odd? Then the graph would cross. Rather than kiss, it would cross. Crosses the x-axis at x equals c. So drawing a little picture of that. I have my x-axis. And let's say c is the c is the 0, or the x-intercept of multiplicity m, and m is an odd multiplicity. That would be something like this. So you'd actually go across the x-intercept. Rather than kissing it, like in the first example, you would cross over. All right, so doing some examples. I'll just do one example here. Just one example. It's pretty easy to get the hang of this. Instructions are to determine the real zeros of the polynomial. After you do that, determine the multiplicity of each 0. And describe the graph's behavior at each 0. Okay, so I'll just do this one here. So I got f of x is my polynomial, and let's say it's factored. It's completely factored. You have 5 times x plus 11 to the second power times x minus 3 times x to the 12th. Okay, so I want to first determine all my real zeros. So I'm going to take this first factor here. That's my red. My second factor I'm going to call yellow. And my third factor here I'm going to call, okay, that was supposed to be yellow. Third factor I'm going to call green. And I'm basically going to initially just look at the part without the exponent on it, the part without the exponent. So I'm going to start with x plus 11 and disregard the exponent for now. I'm going to set that equal to 0. And I'm going to solve for x. So if I subtract 11 from both sides, I get x equals minus 11. So I'm going to say x equals minus 11. X equals minus 11 is going to be a real 0, or an x-intercept you could call it. We're going to use the word real 0 of multiplicity. So now we got to figure out the multiplicity, right? That's the second part, is to figure out the multiplicity of multiplicity. So here the multiplicity is going to be, that's the power up there, multiplicity 2. Multiplicity 2, which is even. So that power is even. So that means the graph is going to kiss the x-axis at x equals minus 11. Why kisses? Because the multiplicity here was even. That power of 2 is an even power. Okay, so we're going to go into our next factor, x minus 3. We're going to set that one equal to 0, and we're going to add 3 to both sides. You get x equals 3. That's going to be, x equals 3 is going to be a real 0 of multiplicity. What's the power above that factor? X minus 3 is understood to have a power of 1 out there. Even though you don't see it, you imagine there's a little power of 1 up there. Multiplicity equal 1, which is odd. 1 is an odd number. Because you have an odd number, your graph is going to cross there at x equals 3. So we say, thus, the graph crosses the x-axis at x equals 1. So y crosses again because we had an odd multiplicity back here. And finally, going to the green, we look at the factor of x, right? Equals 0. Now we don't have to add or subtract anything from that, so we're done. X equals 0, that is our real 0. X equals 0 is a real 0 of multiplicity. What's the multiplicity of x equals 0? Well, if you look at the exponent up here, I'm going to circle that. Multiplicity 12, right? A multiplicity 12, which is even. So that means the graph is going to kiss at x equals 0. The graph kisses the x-axis. x equals 0. So why kisses? Why kisses? Because we had an even multiplicity of 12. Okay, so those are all the zeros. Negative 11, positive 3, and 0. Okay, negative 11, positive 3, and 0. Those are the three real zeros. Or you could call them x-intercepts. All right, so we're going to close this video out, and we're going to do some further analysis of our polynomial functions. We're going to put everything together. We're going to put together the right-hand behavior, the left-hand behavior, and the real zeros, and whether they're kissing or crossing.